We have here first one limit to calculate of a sequence, and in the second case we have to prove that this series is finite, is convergent. The key point of this problem is that if you simply try to evaluate this limit as if this was a continuous variable, just a function, right? Well, this limit does not exist. The reason is 1 plus x squared, the square root of this, grows when x goes to infinity. And you have a divergent argument here, which means that the sign gets oscillating faster and faster as x goes to infinity. So, and approaches nothing, right? However, the trick here, the reason why the sequence does converge whereas the function does not converge, so this does not exist, doesn't exist. The reason is, if you see the argument here, when n is very large, this is equivalent to just n, right? The 1 is negligible with respect to n squared, so this is almost the square root of n squared, which is almost n. So the argument of the sign is pi n, so it's almost pi n. And the sign of pi n is 0. So as n grows, the argument is getting closer and closer to a value of the argument that for which the sign goes to 0. And that's the reason why this goes to 0. And we're going to make this argument formal. And the way to make it formal is to use this Taylor expansion for this function here. Well, don't make mistakes. This is not for this function directly because n goes to infinity and x goes to 0. So we can't apply this to this directly. But what we're going to do is this. We have this function here, and we can factor out the n squared. If we do that, we get pi n here, and then the square root of 1 plus 1 over n squared. And now this can perfectly well play the role of x in this expansion up there. So what we have here is m pi, and then multiply by 1 plus x half, so 1 over 2 n squared, plus, and then this is something that is negligible with respect to 1 over n squared, which is what x is, right? So we have this expansion, okay, which means that this is equal to pi n plus pi over 2n, right, multiplying here, plus O 1 over n, right? Okay, now we have to evaluate the sign of that. Okay, let's call this alpha. So we have the sign of pi n plus alpha, right? And then we have the sign of pi n plus alpha is the sign of pi n times the cosine of alpha plus the cosine of pi n times the sine of alpha. All right. Okay, the sine of pi n is 0, and the cosine of pi n is minus 1 to the n. So this is minus 1 to the n times the sine of alpha. The sine of alpha is this, is pi over 2n plus O 1 over n. All right, now this is the sign of an argument that goes to 0 because when n goes to infinity, this goes to 0. And remember, the sign of x is equal to x plus ox when x goes to 0. All right? So we can use this here, and then the sign of pi square root 1 plus n squared becomes minus 1 to the n. And then the argument, so pi over 2n plus O 1 over n, and then OX. But x is equal to this, right? And this is 1 over n, so the rest is O 1 over n, so it's already included there, so we don't have to add anything more. So this is it, right? And clearly, this is a sequence that goes to 0. Well, we can actually factorize this. This is minus 1 to the n over 2n. Well, let me put it better. It's minus 1 to the n pi over 2n here, plus this gets absorbed there, and then this is 1. Oh, sorry. This is 1 plus O1. Okay, factorizing this factor here. All right. Okay. O1 is something that goes to 0, and this is clearly a sequence that goes to 0. So this sequence goes to 0 when n goes to infinity. So that's the proof of the first of these two items, right? And now we're going to prove the following, the second. And the second is almost a consequence of this, the fact that we have this here, right? What we have here is that the sine is equal to this, so the sine square of pi square root of 1 plus n squared is equal to the square of this. The square of the sine is 1, so what we have is pi squared over 4 n squared, plus something, well, times 1 plus O1, okay? Right? Just, this is the argument of the series here, the square of this, and the square of this is just that. So this is equivalent, right, to pi squared over 4, which is a constant, times 1 over n squared. And the sum of 1 over n squared when n goes from 1 to infinity is convergent. So the sum of this term here from 1 to infinity of the sine of pi square root 1 plus n squared is also a convergent series. It's a convergent series.